Welcome back to some more MP madness with Dr. H. In today's video, what we're going to be focusing on is what happens at the capillary level. This is the microcirculation of blood as it's getting pushed through our blood vessels, pressure and blood flow and all that stuff. You should already have that material behind you. Hopefully you've studied it. But now we've gotten this blood out to the tissues of the body. We get it to our fingertips, we get it to our organs, we get it to our toes. What's going to happen to all of this blood? Okay. Ultimately, it's about making sure that the blood that's carrying these nutrients and the oxygen, right? The nutrients like glucose, the nutrients like amino acids, fatty acids, all the things, the vitamins that our tissues need to survive. We need to get that material out to the cells. All right, so if we start looking at capillaries, hopefully you guys have some background in capillaries already before watching this video, multiple different types of capillaries, like this one that I'm showing here, which is a continuous capillary. So let's go ahead and write that down here. This is an example of a continuous capillary. And there are other different types of capillaries, right? Fenestrated capillaries, sinusoidal capillaries, and as you go up the chain from continuous capillaries, well, those cells get bigger holes, more holes, that sort of stuff. So that's for another lecture to really be able to discuss all that material. And if you take a cross-sectional area of that continuous capillary, you'd be looking at this, and there'd be blood inside of here. Right? What sort of material do we have in the blood? Well, we have oxygen, we have CO2, and those are gases, nonpolar and small. And they're going to be able to diffuse across this cell membrane very rapidly because capillaries have simple squamous epithelial tissue, which is extremely thin, which is going to promote the rate of diffusion across this cell membrane. So all of this oxygen and CO2, it can simply pass via diffusion, right? So it's going to diffuse across that cell membrane. What else is going to be happening out here in the capillaries that we need to know about? Well, also inside of your blood are these wonderful things like electrolytes, right? Sodium, potassium, chloride, and calcium, etc., etc., etc. In addition to sodium and potassium, we have nutrients like glucose, amino acids, and fatty acids. Now, fatty acids are nonpolar, so they're going to have a much better chance of just going through the cell membrane. But things that are charged and molecules that are polar, like amino acids and glucose, they can't just diffuse through the cell membrane. So they're going to need another way to do that. And that's what continuous capillaries are all about, because now this material can simply pass through these cracks. Okay, we're going to see how it's going to get pushed through these cracks. What about other things in our proteins, other things in our blood, like proteins, like large exchangeable proteins, like hormones, insulin, that sort of stuff, right? So if we have hormones, something that we need to get out to the interstitial fluid out here, because remember, this is interstitial fluid, and this in here is going to be ICF. If we need to get hormones out, well, those are going to have to go through some sort of cell-mediated process, like exocytosis and endocytosis. And when it actually goes endocytosis first, as these are going to move through the cell membrane, but it's going to have to work through a process called transcytosis. Okay, now it's going to be able to move those hormones, these large exchangeable proteins, all the way through a cell membrane as a process of endocytosis plus exocytosis is called transcytosis. By the way, I forgot to mention, but the movement of sodium and potassium and glucose through these cracks is called paracellular mechanisms, or a paracellular movement of material. So we're going to go ahead and write that here so you have that too, paracellular. All right, just in case you ever needed that. Now, what about And I'm going to go ahead and change my coloration here because this part's really darn important. What about our blood and the proteins found inside of that blood? So we're going to have lots and lots of plasma proteins inside of that blood. Number one plasma protein is albumin, for instance. And albumin and these other types of plasma proteins are too large to fit through the cracks, and they are not able to be transported through the cells. So these things, well, they aren't going to go through. They're going to stay inside of the cell, and that's important. Okay, so when we're dealing with the green dot right here, we're talking about plasma proteins. And we need those plasma proteins to stay inside of the cell. Why? Because plasma proteins are going to be the number one driver of osmotic pressure. Where does water want to be? It wants to be where the party is at. It wants to be where the particles are at. It wants to be where the proteins are at. It wants to be not where there's more water. Water's boring, so water tries to move. Water's not really boring, by the way. But water tries to move towards where all the particles are at. So when the plasma proteins stay inside of the plasma, water stays inside of the plasma. And that's a really important aspect of all this as well. Awesome. So now we have a pretty good idea of what is going to be getting moved out of our capillaries at the level of the capillaries, but we don't know exactly what's causing these things to move out, other than diffusion, which is just moving through concentration gradients, right? Let's talk about what's happening with the microcirculation at the level of the capillaries. So, to start off with, we know that the heart is pumping, and that heart is pumping blood. We know this. And as that heart pumps blood, we call this cardiac output. And we know that the amount of cardiac output is constantly working in concordance with resistance and blood volume, and it creates a blood pressure. And that blood pressure drives perfusion through our tissues. So when we start thinking about what's happening at the level of the tissues, we say, hey, we got some mean arterial blood pressure. And that mean arterial blood pressure is promoting perfusion. Okay, it's promoting perfusion of those tissues. How does it do that? So that's what I want you guys to start focusing in on. All right, so I did this pre-draw of the capillaries here. So don't forget, terminal arterioles feed into a meta-arteriole. We got our through-fare channel over here on the right-hand side. If we have our precapillary sphincters that are closed, then we have this vascular shunt that's going to allow blood just to flow to the other side. So all of this is in a previous YouTube video, of course. These are our true capillaries, and they branch off. I drew this big capillary down here, so I have more room to draw inside of it. All right, so blood pressure is pushing blood through these tubes. Okay, so from the terminal arteriole, that blood now is going to move into the meta-arteriole. And this blood pressure is constantly pushing against the walls, hence blood pressure. And as it pushes against the walls, it's going to be trying to stretch those walls out, right? We've always just called it blood pressure in the past, but there's actually a better name for it, and that's called hydrostatic pressure. Hydrostatic pressure. Hydrostatic pressure, which is the pressure of fluid pushing against the wall. It doesn't matter whether it's a blood vessel wall, any wall, right? There's hydrostatic pressure inside of the plumbing in your house. Hydrostatic pressure is fluid pushing against the walls. And hydrostatic pressure, as it pushes against the walls and it makes it to these capillaries with cracks in it, what that's going to end up doing is it's going to promote, because we got lots of pressure inside of this capillary, it's going to promote the movement of materials through these cracks. Okay, this is called filtration. It's going to promote the movement of materials through these cracks. So what I'm going to do is I'm just going to draw a real simple diagram that kind of tries to describe this as a side view. So if we take and we look at our capillaries, right? These big long capillaries are going to have some cracks in them. They're going to have some cracks in them. And as we push out material from the inside of our blood to the outside, we call this filtration. So I'm just going to write that down as an F, and F equals filtration. Awesome. Now, at the same time, there are going to be things that are trying to draw material back into your blood, like, for instance, albumin, which we'll get back to. All right, and it's the movement of material back in the blood, it's opposing filtration. This is called reabsorption. Okay, so we're going to have filtration and we're going to have reabsorption. Where filtration is the movement of material out of the blood, reabsorption is the movement of material back into the blood. Nice. We're starting to get somewhere. So now what I want you guys to do is go back and go, we have our hydrostatic pressure here, which in essence is the same thing as saying mean arterial blood pressure, more or less. It's the mean arterial pressure that's going to be creating this hydrostatic pressure found inside of the blood. And as this enters these big true capillaries, what's going to end up happening is that the pushing of fluid against these walls is going to promote the movement of material through these capillaries, out of the capillaries into the interstitial fluid down below. We call this hydrostatic pressure, but we need to be even more specific because hydrostatic pressure is just the pushing of fluid against walls. We're going to have hydrostatic pressure out in the interstitial fluid as well. That can potentially push backwards. So we need to specify that this hydrostatic pressure is found inside of the blood, and we're going to do that with the subset B. So hydrostatic pressure in the blood, we're going to call that HPb. Okay, hydrostatic pressure inside of the blood. And what do we know about this? Does this hydrostatic pressure inside of the blood, let's start changing our colors up here just to make this, I don't know, prettier in general, right? What do we know about hydrostatic pressure inside of the blood? Is it promoting filtration or is it promoting reabsorption? Hopefully you guys immediately saw it's pushing things out of the blood. Therefore, we can say this promotes filtration. All right, next. Fluid outside of the cell is interstitial fluid, but this interstitial fluid can actually push back. Now, this interstitial fluid actually tends to be negligible, right? There doesn't tend to be a very high hydrostatic pressure out here in the interstitial fluid. But let's go ahead and write it out. Hydrostatic pressure in the interstitial fluid. If this value was great, what would happen to the pressure pushing back? It would increase. Does this pressure promote filtration or does it promote reabsorption? Hopefully you guys see it's pushing back, trying to move things back into the capillary beds. So this is promoting reabsorption. Awesome. That's two variables that we wanted to talk about. But there's another variable that we want to talk about, which I started talking about over here, which is the fact that your blood constantly has proteins in it, right? Most of these proteins are produced by the liver. So the liver is going to have a huge impact in the concentration of proteins in the blood. And those proteins get down into these capillary beds. But what do we know about them? They shouldn't leave the blood. So when we're starting to look at these pressures created by proteins, well, protein in a fluid is called a colloid, right? So proteins inside of the fluid is called a colloid. And the movement of water is driven by osmotic pressure. And colloids tend to create a very high osmotic pressure. Osmotic pressure is also often known as oncotic, O-N-cotic, right? Oncotic pressure in medical situations. You'll hear oncotic pressure quite a bit, represented by the Greek letter pi, not 3.14, but just pi. It's a little confusing. But we're going to go ahead and abbreviate this as COP, colloid osmotic pressure. So there's going to be a bunch of colloid osmotic pressure inside of the blood. So let's go ahead and differentiate that. What did we learn? Where does water want to be? It wants to be where the party is at. And the number one party in the blood, yeah, that's right, is colloid osmotic pressure created by albumin. Okay, the number one source of osmotic pressure in the blood is albumin. It accounts for a very large percent of the overall oncotic pressure. Over 75% of the oncotic pressure is created by albumin. So what do we see? Does that promote filtration or does that promote reabsorption? That promotes reabsorption, right? Last but not least, what if a little bit of protein is being made by the cells in the interstitial fluid? Or what if some protein moves from the blood out into the interstitial fluid? Well, then we're going to have some proteins out here, which we're going to call colloid osmotic pressure. But of course, it's in the interstitial fluid, so we're going to write IF. That is going to draw some water towards it. Colloid osmotic pressure in the interstitial fluid. Does that promote filtration or does that promote reabsorption? That promotes filtration. Okay, if there were proteins out in the interstitial fluid, it would promote filtration. Awesome. Sweet. What does this all mean? What are we doing here, Dr. H? I don't know. Listen, we're going to end up tying all these variables together to try to understand when filtration occurs versus when reabsorption occurs. We want to talk about the sum of all the filtration, both on the arterial side of things and on the venule side of things. Okay, in order to do that, we're going to look at the sum or the net filtration pressure. Okay, there's net filtration pressure. Again, in the arterioles, there's net filtration pressure in the venules. And you can end up writing that out as NFP arterial or NFP venule. That's okay. But personally, I like to just write down, okay, it's net filtration pressure. And if we end up with a value that promotes filtration, we're going to end up with what's called a positive value. We're going to have net filtration, right? We're going to have net filtration, hence net filtration pressure. And what you guys are going to see is we're going to create a formula here. And if that formula is positive, if it's positive, what do we know is going to happen? This is net filtration pressure. So if the value that we're about ready to go about calculating is positive, then we know that it promotes filtration. But what if this value ends up being negative? Then it's going to end up promoting reabsorption. Let's tie that back in with our equation over here. Net filtration pressure. The number one value that controls filtration, the number one most important value that controls filtration is hydrostatic pressure inside of the blood. This is driven by your mean arterial blood pressure. We can think of them synonymously. So what we're going to do is we're going to put that into our formula first. And since it promotes filtration, we're not going to put a negative sign in front of it. We're going to have a positive sign, but the positive sign at the beginning of your equation, you just don't put any sign, and that tells you that's a positive value. This is the most important. This will be the highest value. It's going to be the most important thing that drives filtration. Now, what comes next? Let's go ahead and talk about hydrostatic pressure. Hydrostatic pressure in the interstitial fluid. And what do we know about hydrostatic pressure in the interstitial fluid? is it promotes reabsorption. And reabsorption does the opposite of filtration. So we're going to subtract that from hydrostatic pressure in the blood because it's opposing hydrostatic pressure in the blood. So now we're going to throw in some hydrostatic pressure in the interstitial fluid, and that's going to oppose hydrostatic pressure inside that blood. What else is opposing hydrostatic pressure in the blood? What else is doing the opposite? Well, that's going to be colloid osmotic pressure inside of that blood, right? That is constantly drawing fluids back to it. So it's opposing filtration. Last but not least, well, we have another thing promoting filtration over here, and that is colloid osmotic pressure in the interstitial fluid. And we can add that back to the value that we get here because it's going to promote a little bit of fluid moving out into the tissues. Awesome. What does this all mean? What does this all mean? I'm trying to find. Go ahead and use this one here. So what we're going to do is we're going to do some calculations. We need to first look at hydrostatic pressure in the blood. The typical hydrostatic pressure in the blood is approximately 35 millimeters of mercury as it enters this capillary bed. So here at the beginning of the capillary bed, the hydrostatic pressure inside the blood is approximately 35 millimeters of mercury. Okay, that's the pushing pressure, promoting filtration. Cool. So we're going to go ahead and write that in down here. We're going to say NFP on the arterial side of things is equal to 35 millimeters of mercury. Let's fill in the rest of this. Well, hydrostatic pressure in the interstitial fluid in a healthy patient should be negligible. It should be 0 millimeters of mercury. There shouldn't be a large pressure inside of the tissue. If pressure in the tissue builds up, we call this edema. We don't want that, right? So this value here should typically be 0, somewhere between 0 to like 1 millimeters of mercury. Very small value. What about colloid osmotic pressure in the blood? All of this protein that's in the blood, the colloid osmotic pressure inside of the blood, well, there is a lot of colloid. And in fact, albumin alone accounts for about 22 millimeters of mercury. But the total colloid osmotic pressure is around 25 to 28 millimeters of mercury. And for ease of things, we're going to go ahead and write 25 millimeters of mercury in this video. Okay? Your professor's going to change this value on your test anyway, so you might as well learn it in lots of different ways. Colloid osmotic pressure in the blood is 25 millimeters of mercury. This is the pulling pressure. This is promoting reabsorption. So we're going to subtract it from the original hydrostatic pressure in the blood. Last but not least, we're going to have some colloid osmotic pressure out here. It's a very small value, typically around 1 millimeters of mercury tops, okay, in a healthy patient. This can change. This can definitely change. We'll talk about how we change this in just a second. Okay, so now let's do the math on all this. 35 minus 22 is 13. Add 1 back to that, we have 14. So when we were looking at NFPA, and we end up saying this is 14 millimeters of mercury, is that a positive value or is that a negative value? If positive, what do we know is happening to the net filtration? If it's positive, then we have net filtration. And that's exactly why on the arterial side of things, materials will move from the blood into the tissues, is because we have net filtration. Let's look at what happens on the venule side of things. As blood moves through the capillaries and as it spreads out over this very large surface area, and the velocity of that blood decreases and fluid gets filtered out, the hydrostatic pressure on the other side of this and throughout this capillary bed where the surface area is highest, it's dropping. Okay, it just continues to drop and drop and drop. There's all sorts of values you're going to find in your books for this. anywhere between 14 millimeters of mercury to 20 millimeters of mercury. Let's just go ahead and write approximately 15 millimeters of mercury just to make it easier. It tends to be on average more like 16 millimeters of mercury. But again, your professor is going to change this value on you anyway, so you might as well learn it in multiple different ways. So the hydrostatic pressure in the blood is going to be approximately 15 millimeters of mercury. But what do we know about colloid osmotic pressure in the blood? Should we be losing proteins from the blood to the tissues? The answer is no. No, heck no, right? So what do we know the colloid osmotic pressure in the blood on the venule side of things should be? It shouldn't have changed. There should be no difference going on over here. So when we look at the net filtration pressure, on the venule side of things, the hydrostatic pressure in the blood is going to be 15 millimeters of mercury. Hydrostatic pressure in the interstitial fluid should still be approximately 0 millimeters of mercury because that shouldn't have changed too much. Oh, that's interesting. I wrote 22 here. That's because normally I teach my students it's 22 for albumin. I apologize. So 10 plus 1 is 11. You guys get the point, though. It's still a positive value. Sorry about that. So we're going to go ahead and average out 25 millimeters of mercury. Hence crazy with Dr. H, right? We got madness going on here. And then we'll go ahead and add back that 1 millimeter of mercury related to that colloid osmotic pressure in that interstitial fluid. Now, let's do the math here. You'll see we have a negative 10, add 1 back to it. So now we have a negative 9 millimeters of mercury. And if the final value is negative, what do we know about it? On the venule side of things, we're promoting reabsorption. It's pretty cool, right? So now on the arterial side of things, we're promoting net filtration. And on the venule side of things, we're promoting net reabsorption, which is exactly what we want. Because on the venule side of things, we are picking up CO2, we are picking up metabolic waste, and we're pulling some of the fluid back into the system. Do you guys notice that it doesn't pull all the fluid back into the system, though? You see that there's actually a difference between net filtration and net reabsorption? That means that fluid is going to start building up in the interstitial tissues unless we do something about it. What do we have in place to do something about this? We have the lymphatic system. So we have lymphatic capillaries down on this side. The lymphatic capillaries have valves. Lymphatic capillaries, and they have valves. And what do we know opens valves? Pressures, right? So if the pressure is greater out here than inside of the lymphatic capillary, that's going to drain that excess fluid back into it. And that becomes lymph. And then that is going to move back through the lymphatic system, through the lymphatic collecting ducts into the lymph nodes. And you guys will see that in a lymphatic video. But that will be important when we start talking about potential diseases that can impact this system. Awesome. I hope this part of this lecture helped you, right? Because what we're after here is, does filtration occur? Does reabsorption occur? And what is the sum of the product of all these things that promote filtration versus promoting reabsorption? What does the sum end up resulting in? Because now, I think one of the easiest ways to learn is to break stuff. Let's break this. Let's look at what would happen in a diseased patient. Okay? What sort of diseases can we look at? Let's look at a patient that is peeing out too many proteins. Okay, they have something that's causing them to pee out proteins, whether it's some sort of kidney damage, they've had hypertension for a little bit, now they have some kidney damage, and they start to lose proteins. So which value do you know is going to be impacted as we end up having something like hypoalbuminemia? which value is going to be affected by hypoalbuminemia? Okay, low levels of albumin in the blood, which value is going to be affected? Hopefully you guys are immediately saying albumin is all about colloid osmotic pressure. This is the #1 driver of colloid osmotic pressure. So albumin acts on the colloid osmotic pressure here. Hypoalbuminemia, what's going to happen to the colloid osmotic pressure? That colloid osmotic pressure is going to decrease. And as the colloid osmotic pressure in the blood decreases, we have less reabsorption power. We're going to decrease the amount of this reabsorption power here. So what does that do? When we get rid of reabsorption power, we promote more filtration. Okay, when a negative value decreases, it actually makes the left side of the equation bigger. And you can go down here and do that mathematically as well. Say, for instance, this 25 turned to 20. Now it's 35 minus 20 is 15. So that number, the net filtration number, just got bigger. So in hypoalbuminemia, we're going to see more fluid going into the tissues, which causes edema. What else do we have going on? Let's go and talk a little bit even more about proteins, right? What about somebody with severe malnutrition? Now, severe malnutrition, we got to think about what's happening in this patient that's not eating properly. They're not getting enough proteins in their diet. They're not getting enough fats in their diet. They're not even getting enough glucose in their diet. But of those, which one of those nutrients is going to impact this equation? It's got to be proteins, right? Proteins is going to have a huge impact on this equation. And severe malnutrition, the number of circulating plasma proteins starts to decrease because they're not consuming them, so their body can't make them. So that again is going to impact that colloid osmotic pressure in the blood. All right, what else do we have going on here? What happens if there's a lymphatic block? What if we have way up here, there'd be, say, a lymph node or a lymphatic collecting vessel or something like that, and we block that. We had an occlusion, whether it's due to a tumor or some sort of inflammation, some sort of lymphedema, right? So if we block this, what's going to end up happening is fluid is going to back up and go the other way, right? So this fluid can no longer leave the tissues. Instead, the fluid starts to go backwards. So which of these values is going to be impacted by this lymphatic block? Well, as fluid builds up out here, fluid is hydrostatic pressure, right? So fluid in the interstitial fluid starts to build up. This causes edema in that tissue as that fluid builds up because we can't get rid of it. And the hydrostatic pressure in interstitial fluid is going to start to increase. But so is colloid osmotic pressure in the interstitial fluid because we can't get rid of this stuff. So net effect is going to be an increase in the edema. It's going to initially try to increase the amount of reabsorption, but everything's going to be impacted in that patient in the long run. What else? Any sort of liver disease affects protein concentration. Let's go and start talking about the heart. What about in heart failure? Well, we know that heart failure impacts mean arterial blood pressure, right? And heart failure does that because mean arterial blood pressure is proportional to cardiac output times TPR times blood volume. So if somebody has heart failure, that cardiac output starts to drop. And if that cardiac output drops, mean arterial blood pressure drops. And if mean arterial blood pressure drops, the hydrostatic pressure in the blood will be impacted, right? Now we're going to start to see a decrease in the amount of hydrostatic pressure in the blood. And that's going to, depending on where you are in the body, it's going to decrease filtration. But that's not the end of the story for heart failure, unfortunately, because again, it depends on the tissues you're at in your body. What if you're in the legs? which so far away from the heart. What just happened to the blood pressure out in the legs? It dropped so low that in essence you don't get any filtration at first. But then we can't get that blood back to our heart because we have a heart failure patient. So there's just not enough blood pressure to get that blood back to the heart. So what's going to start happening to blood building up into the legs of those patients? Blood is going to start to build up in the legs of those patients. And as it does, that hydrostatic pressure in the blood starts to go back up again due to the pooling of that blood. And that's going to promote that blood to go out into the tissues of that patient. You start seeing a lot of peripheral edema, especially in the legs of those patients. Pretty bizarre. Versus other locations like around the chest, around the torso, you're not going to get the perfusion that you should get there. So you're going to get a decrease in edema in those locations. Not the pulmonary, of course. There's going to be pulmonary edema, especially in congestive heart failure. But just trying to get you guys to think about the fact that different disease states are going to impact this equation differently. And it's important to think about each one. What about in dehydration? Somebody is severely dehydrated. Again, the mean arterial blood pressure starts to drop because the blood volume is low in those patients. And so as that mean arterial blood pressure drops, there's less hydrostatic pressure pushing against the walls. And as hydrostatic pressure in the blood decreases, net filtration pressure decreases. That's how we can use this. That's how your professors are going to test you. I recommend that you guys write this out, break it, or enhance it. There you go. Microcirculation in the capillaries. I sure hope this was helpful. All right. If your professors don't go into pathophysiology at all, then you can ignore all that. You're welcome. Most professors will, though. All right. That is it for this particular lecture. Crazy. The crazy is currently over until the next video. All right. Humankind, be both.